Hi everyone, for this video we're going to talk about the different types of discontinuity. So let's start with the whole discontinuity. So this discontinuity occurs when there is a hole in the graph of the function. So for example, we have this there. So there is a hole. So we learned before that when there is a hole in the graph, it is discontinuous. Okay. And this whole discontinuity is also what we call a removable discontinuity. Okay, it means that we can redefine the function to remove this discontinuity, this part, this hole. Okay, and example of this would be something like, let's say if we have a function of x squared minus 1 over x minus 1. Okay, so in this case, if we plug in x is equal to 1, it will be 0 over 0, which is indeterminate. Okay, so it does not exist. So it means that it is discontinuous at x is equal to 1. Therefore, our x should not be equal to 1. Okay, but then we can remove the discontinuity by, let's say, factoring. Okay, so x squared minus 1 is the difference of two squares, and the factors are x minus 1 and x plus 1. Okay, all over x minus 1. So we can cancel this out. So you're left with x plus 1, in which we removed the discontinuity. Okay, that's why a whole discontinuity is a removable. Okay, let's go to the next one, which is jump discontinuity. So this one occurs when the graph of the function stops at one point. So let's have this, for example, and at one point, and then jump to another point. Okay, so that is a jump discontinuity. So both left and right hand limits exist, but they're not equal. So if we're going to check from our left hand side as we approach 0, all right, this value, let's say this is 3, so that's equal to 3. Whereas for the right hand limit, okay, so as we approach 0, okay, so the value is, let's say, 1. So the right hand limit and the left hand limit exist, but they're not equal. So this is a jump discontinuity. Okay, the next one is the infinite or asymptotic discontinuity. Okay, so in this type of discontinuity, at least one of the two limits is infinite. It has a vertical asymptote. Okay, so for example, we have a function 1 over x minus 1. Okay, so it means, so if you graph this, so it will look like that. Okay, so if you look at our left hand side limit, so as you approach that, okay, you will have a negative infinity. Okay, and for our right hand limit, so the value of the limit will approach positive infinity. Okay, there. So also note that jump discontinuity and the infinite or asymptotic discontinuity are non-removable. Non-removable. Okay, infinite is also non-removable. So only the whole discontinuity is removable. So let's try some examples in identifying or classifying discontinuity. So determine whether this function is continuous or not, and if they're not, classify them as removable, non-removable, is it jump, or an infinite or asymptotic discontinuity. So we have f of x is equal to x squared minus 9 over x minus 3. So we know that if x is equal to 3, our function will be 0 over 0, which is indeterminate. Okay, so if it's indeterminate, it is discontinuous. Okay, it is discontinuous at x equals 3. So if we graph this, okay, it will look something like that. Let's make it a whole. Okay, there you go. So there is a whole, and therefore, so it's a whole discontinuity, and it's removable. Okay, so if it's removable, okay, let's remove the discontinuity by redefining the function. So how do we redefine this function? So the limit of the function as x approaches 3, so we have x squared minus 9 over x minus 3. Okay, so x squared minus 9 is difference of 2 squares, so factoring that, we have x minus 3 and x plus 3 over x minus 3, so we can cancel x minus 3. Therefore, we have the limit of the function f of x as x approaches 3 is equal to x plus 3. So let's substitute, will be 3 plus 3, and that would be equal to 6. So we were able to remove the discontinuity at x is equal to 3 by redefining the function. Okay, so we can write that as f of x is equal to x squared minus 9 over x minus 3 if x is not equal to 3, and it's equal to 6 if x is equal to 3. So by graphing, our function will now look like something like this. There. Okay, so we redefine the function. Okay, next one. Okay, f of x is equal to x squared plus 1 if x is greater than 1, and x minus 1 if x is less than or equal to 1 at x equals 1. So let's start by identifying if the limit exists at x is equal to 1. So if it's equal to 1, we will use x minus 1. So 1 minus 1 is 0. So it exists. Okay. Next, let's do and find if the right hand side limit and left hand side limit exist and they are equal. So f of x, as x approaches 1 from the left, so left hand side limit. So if it's from the left, it means less than 1. So we'll use again x minus 1. So that's 1 minus 1, so 0. Okay, so that's good. That's looking good. Now let's have the right hand side limit. So it's at x approaches 1 from the right positive. So in that case, if greater than 1, we'll use x squared plus 1. So x squared plus 1 is 1 times 1. 1 squared is 1. So 1 plus 1 is 2. So we can see here that the right hand side and the left hand side limit exist, but they're not equal. Therefore, it is discontinuous. And because of that, this is a jump discontinuity, and it is non-removable. Okay, let's try this one. F of x is equal to x squared plus 3 over x squared plus x minus 12 at x is equal to 3. So let's check first if f of 3 exists. Okay, so 3 squared plus 3 over 3 squared plus 3 minus 12. So 3 squared is 9 plus 3. So 9 plus 3 minus 12. So this is 12 over 12 minus 12. So we have 12 over 0. So it means this is undefined, okay, not indeterminate. So indeterminate is if we get 0 over 0, okay. But this is undefined because we have a denominator of 0. So therefore, this is an infinite discontinuity or asymptotic discontinuity, which is a non-removable discontinuity. All right, because we have an asymptote at x is equal to 3.